Hi, welcome back to Reconstructing Relativity. This is Ted Cole, and this will be Chapter 7. There's so many things I want to talk about today, but I'm going to have to take them one at a time. I want to talk about science and philosophy. We're going to revisit the Michelson-Morley Experiment that we did a couple videos back, and I've got some new animations for that. I'm going to try to bring together a lot of pieces, a lot of things that have been presented in earlier videos. And so if you haven't seen my earlier videos, I recommend you go back and check them out in sequence and bring you up to date. Otherwise, let's get going. Now, this new constructive model viewpoint that I'm developing here is not, as I said before, is not a challenge to Einstein's scientific results at all. But it is a challenge to some of the philosophical foundations of it and some of the ongoing philosophical implications. So we need to be clear about the difference between science and philosophy. Philosophy means love of wisdom, and it's all-encompassing. And so, since it's all-encompassing, it must include science as a branch of philosophy. I mean, science doesn't talk about art or love or many other things that science doesn't really get into. Science is it a branch of philosophy? They call themselves PhDs, the doctors of philosophy. So it seemed to be that science is a part of philosophy, but science on a whole often discredits philosophy because the values of science are in measurable and repeatable facts. And so science tends to discredit philosophy because it deals in speculation, things that aren't provable. It's good for arguments, but it doesn't really settle anything. And so there's some way in which science considers itself to be philosophy. It is since its values what is real, everything that isn't fall under its purview isn't really significant in terms of a philosophical outlook. I mean, measurement is key to science. Yes, there's a scientific method. You hypothesize what you expect will happen in a certain situation, and then you test it, and you make a measurement and see if your hypothesis is right or wrong. And you can learn, and you can rely on it. Science is great when scientists measure objects of interest. It could be inanimate, natural objects, created objects. The entire Industrial Revolution came out of science when Galileo started measuring things instead of just taking Aristotle's word for it. That was the dawn of science. So science is great in so many situations. It's done so many things for us. I love science, but science is not as great when the subject and object are intertwined. That's why they call them the soft sciences. Anthropology, psychology, sociology. Well, we know why those are soft sciences. It's because people who are raised and educated in cultures want to go study and make measurements of other people who are raised differently in different cultures. Well, it's difficult, if not impossible, to be objective. You can't remove yourself from the situation sufficiently to not have some biases going in and biases coming out. And so any good scientists, there's still value in these things, but the scientists in these soft sciences have to really look at themselves and their culture and their history in order to best understand what they're measuring. When scientists started measuring light, they unknowingly got into some areas where the usual subject-object relationship broke down. In relativity, what happens to light also happens to us. and everything around us. But they did not know that at the time. Remember the Michelson-Morley Experiment? They used this swimming metaphor in an attempt to measure the speed of the Earth through space, knowing that light traveling across ether wind, the space that was flowing past us, would take a different amount of time to make us a round trip than light traveling upstream and downstream through that ether wind. They set up this instrument to comparatively measure the speeds in those two directions. And the differences were so small in time that they planned to use this interferometer. The waves returning would not quite line up the way they left. And so then they planned to turn the instrument and see the waves, the direction of longer time would become the direction of shorter time. And so doing, the waves would have to walk past each other, and that would represent as fringes, which they could then count and calculate back to what the velocity of Earth must be through space. But it didn't work out. So as scientists, here's what they expected would happen. First, let me show you the setup they've got. This represents the interferometer. The yellow dot is the light that's going to be split into two pieces, and part of it's going to go up, and part of it's going to go to the right. They both go the same distance, and at the end of that distance, they hit a mirror, and they come back and return. And if there was, say, the Earth moving towards the right through space, then here's what they expect would happen. Go. All right, so the dot of light going up and coming back will go the same speed in both directions, but the one going to the right is going into the wind, but then coming back, it's coming with the wind, the wind of space. But mathematically, the times for those two paths are not the same, so one light should come back before the other. Now, you couldn't tell at first which one went faster, but what they would do then was take this whole apparatus, which was floating in a vat of mercury, and spin it slowly through 90 degrees, which would make the faster path become the slower path, and the slower path become the faster path. And as those exchanged, the waves would have to pass each other, and they'd see these fringe patterns, and they would count the fringes, and they'd be able to calculate what the time difference was for the two different paths, and therefore work out what the speed of Earth through space was. But it just didn't work. Here's what happened. Even if you have a sharp eye, you might not be able to see in this picture what the difference is. But the light came back at the same time, and it didn't matter. They could turn the device, the two times for the two paths were the same. It didn't matter. They couldn't get any fringes to move at all. Well, here's a side-by-side of the final picture, and you can see I used a gamma of 1.0336, which is much larger than what the Earth would actually experience going through space at the speed it does. Probably, we don't really know because we can't measure it, but it's large enough so that you could see the difference in the end times. But the difference is over here, that in the direction of motion, which is left to right, the apparatus got shorter, a little bit shorter, and affected the times. We'll show more higher gammas to show how this works even more. So here's a higher speed case, just over half the speed of light. V over C is 0.515, gamma is 1.167. So now in my picture, you're seeing a noticeable shortening on the left to right axis of that arm of the interferometer. Notice, however, and we'll talk about this more, Michelson's clock reads 30 when the cycle is completed, and I'm putting down here Michelson's distance is 30. So more discussion on the next one. We're going to go even faster. Okay, so now we're going to go really fast. This is our old friend V over C equals 0.866, which gives us a gamma of 2.0. So now we can really see the shortening, and we can really see the clock, that Michelson's clock runs at half the speed, because gamma is 2. His clock runs at half the speed of the universe clock. And yet, Michelson's clock reads 30, just like it did before in every other case. And Michelson's meter stick says that it went 15 meters out and 15 meters back. Although in the universe scale, we're seeing 7.5 out and 7.5 back. But this is what's happening in reality. Michelson's not in Kansas anymore. He's not even in Ohio anymore. Michelson's got this thing on a high-speed rocket ship running through space at 86.6% of the speed of light, and still he's measuring the same speed of light on a round trip in both directions, perpendicular directions, and regardless of the speed he's going, he's still getting the same answer. Incredible. Remember back in an earlier video, we were talking about Einstein's formal principle, which was that every observer would measure the speed of light in a vacuum to be the same, regardless of their motion, whether they were going towards the light super, super fast or away from it super fast, or sitting on Earth. A flash of light comes by, everybody measures the speed of it to be the same. That's the formal principle, but it wasn't understood how, at that time, we were like, how can that possibly be true? Well, now we're starting to get an idea of how that could be true. And the key word in that sentence is measure. Everyone measures the speed of light to be the same. So we have to examine this process of measurement very carefully and consider what's going on physically to make the measurements come out the same. So our constructive model view is that all observers always measure the same speed of light in their frame of reference because their clocks run at different rates depending on their own speed through space, and their lengths of their measuring equipment in the direction of motion is also affected by their own speed. But they cannot observe or measure these changes. That's the key. Everything looks the same. Everything feels the same. The clock looks the same. Can't notice that because you are a part of it too. Your thought process is slowed down. Your breathing is slowed down. Your arms are shorter in the direction of motion. Your meter stick is shorter in the direction of motion. That's the phenomenon that is causing these things, but Einstein just simplified it. Didn't have this constructive model, so he just went the other way. You might remember back in my second video, I quoted Einstein where he said he couldn't come up with a constructive model that sorted out what was going on, so only a formal principle could move things forward. And the formal principle is simply that all observers will measure the speed of light to be the same in a vacuum. So he took that as a starting point without really understanding what the physical phenomenon was. And he went forward and did the math and got these results that comparing two different observers in motion relative to each other, both will measure the time in the other reference frame to run slower than their own time, and both will measure lengths in the direction of motion in the other frame to be shorter than their own lengths. So how's that work? Does our constructive model explain that? Well, not yet. We'll get there. We'll definitely get there, and we'll understand it better. But I'll just give you one more hint, and then we'll be out on this one. So here's the teaser / hint. Our Michelson-Morley model clearly showed that the light beam's round trip would always be the same regardless of direction or speed through space. But Einstein said that the one-way speed of light will always be measured to be the same. How can that be? Clearly, going to the right and coming back to the left took different amounts of time, right? And again, he was right. But the key word there is measured. We'll sort that out starting in the next video. As always, thanks for watching. Please like, subscribe, share this video. Here's some GIFs that were left over. Just put them here for your visual entertainment as we outro with part of a song by World Party, part of a song by Part of World Party called Is It Like Today?
Yeah, I really want to know about this. Is it like today? Oh, whoa. Then there came a day, it moved out across the Mediterranean, came to Western Isles and the Greek young men. And with their silver beards, they laughed at the unknown of the universe. They could just sit and guess God's name. They said, how could it come to this? We're really worried about living. How did it come to this? Yeah, we really want to know about this. Is it like today? Oh.